Dr. Chip Conrad present to us on heat illness, specifically in rural populations, which is an area that we've been trying to focus more of our climate and health advocacy work around. And we're very excited that today's webinar is co-sponsored by our partners in Georgia and North Carolina. Georgia Clinicians for Climate Action and North Carolina Clinicians for Climate Action. The heat illness is a great topic to be focusing on as we enter these summer months, and very timely for Virginia, as this week we were just encouraging advocacy towards the Virginia Health and Safety Board that is currently considering some regulations for outdoor workers as well as indoor workers related to heat illness. All participants today will be in listen-only mode throughout the presentation, but we invite you to submit questions using the Q&A box in your Zoom menu throughout the presentation today. We will be getting to questions in the last 10 to 15 minutes of the hour-long presentation. And I should also mention that the presenter today, Dr. Conrad, has no conflicts of interest as a part of this webinar, which is going to be available for CME credits, and you will all be receiving instructions tomorrow following this webinar for how to apply CME credits for your attendance today if you're interested in that. With that, I'll turn it over to VCCA's board chair, Dr. Samantha Dute, to introduce our speaker.
Well, thank you, John. And I am so pleased that Virginia Clinicians for Climate Action is co-hosting today's event with Georgia Clinicians for Climate Action and North Carolina Clinicians for Climate Action. Clearly, the health impacts of our changing climate don't obey state lines, but are experienced often regionally. And I can't think of a better topic to view through a regional lens than the impacts of rising temperatures and heat illness. So with that, I'd like to invite introduce our speaker for today. We're delighted to have Dr. Chip Conrad with us today. Dr. Conrad is a professor in the Geography Department at UNC Chapel Hill and the director of the NOAA-funded Southeast Regional Climate Center that provides a wide range of weather and climate services and expertise for the region. Dr. Conrad is a geographer, meteorologist, and a climatologist who studies extreme weather and its impacts on society. He has expertise across a wide range of areas in climatology and meteorology, including heavy precipitation, tornadoes, hurricanes, cold air outbreaks, winter weather, and climate change. So with that, I am pleased to pass the microphone to Dr. Conrad.
Okay, well, thank you very much. It's a real privilege to be here, and it's great to hear that we have people from North Carolina and also from Georgia. And so I'm going to really do the best I can to try to tailor the talk to the broader Southeast. Okay, and I just want to confirm that you can see my screen. Okay, so the title of my talk is The Geographic Patterns of Heat Illness in Rural Southeast U.S. and the Factors that Control its Incidence. And so here's just a bit of an outline of what I'm going to cover here. I'm going to start off just very broad, just looking at heat stress. And I'm going to kind of start off from a climatological perspective, give some background there. We're all used to thinking about, heat in terms of temperature. Living in the Southeast, of course, a lot of us are very familiar with heat index, but a lot of our research has been around wet bulb globe temperature, and that more and more is becoming really the best measure of heat stress. And so I'm going to talk a little bit about that. And then I'm going to go in and I'm going to show you lots of maps that show how heat stress, specifically wet bulb globe temperature, how it varies across the Southeast U.S. And I'm going to teach you a little bit of basic climate too, a little bit about why we see the patterns that we see in terms of heat stress. And so that's very much a broad scale perspective. And then we're going to kind of zoom into the local scale where our research has revealed that there are very marked variations in wet bulb globe temperature and heat stress in a landscape. And Obviously, if you're in the shade, it's somewhat cooler and less dangerous than you're in the sunlight. But our research reveals that wind speed plays a huge factor. And if you walk around a landscape, you'll find very marked variations of wind speed. And we find that that has a big influence on wet bulb globe temperature or heat stress. And then we're going to go into heat vulnerability, and I'm going to share some research that was done a couple of years ago. I'm going to share with you some of the patterns that we found in heat vulnerability across North Carolina. And I'm going to make some inferences across the broader Southeast. And I'll talk about the factors that we hypothesize are controlling these patterns of heat vulnerability. And of course, what you're going to see there is that the rural areas really, really stand out compared to the urban areas. And in the last part, I'm going to just speak a little bit about reducing heat stress and vulnerability. My focus is going to be on basically a web-based tool, a heat stress prediction tool that we've developed. And it's a tool that now works for the broader Southeast. And so I'm going to actually give you a demo on how to use that, basically how to use that tool. And of course, it's very timely with the heat that we've had. But I'm also, as I'm sharing that tool, I'm going to tell you how it's being used, specifically how it's being used to mitigate against heat exposure for high school athletes. To this point, that's been our focus and engagement as high school athletics. And in the coming years, we're going to be engaging more and more with other groups. And so I'm hoping this might be a bit of a launch point for that. Okay, so just real quickly, just quickly promote the Southeast Regional Climate Center. It's funded by NOAA. We do a lot of different things. We're one of 6 centers scattered out across the country. You see our geographic footprint there in the map on the right. But we do a lot of things. We engage with communities and stakeholders a whole lot to really learn what people need in terms of weather and climate information. And we're experts in terms of weather and climate data, so we know a lot about biases. That kind of gets into climate change too, which I'll say a few things about. But another thing we do is we develop web-based decision support tools. So we go out in the community and we learn what people need, and then we build tools that effectively translate weather and climate data into information that's useful. And then lastly, we educate stakeholders like I'm doing here on emerging regional climate issues. And heat, is definitely an issue that's getting more attention these days. I'm also affiliated, a co-PI with the NOAA-funded Carolinas Integrated Science and Assessments Program, CISA. And we advance scientific understanding of climate processes and their impacts, focused in the Carolinas with applications in other parts of the Southeast. We provide decision support through the development of targeted and tailored information. And our overarching charge really is to advance climate adaptation, particularly in this era, which we have a change in climate. So speaking of that, I thought I would just start off with a few maps here showing changes in temperatures. And so this shows the average annual frequency of days in which the air temperature exceeds 100 degrees. And so if you look at the map panel on the top left there, you see the areas of orange. Phoenix is pointed out there. It's sort of the poster child, at least in terms of big cities, for extreme heat at 92 days. And you see Dallas is also pointed out there at 15. And so if there's a lot of different basically projections of climate change out there, and if we go with basically the one around business as usual, in other words, if we don't make changes in our carbon footprint in the coming years, and we look at the models and we look at the more aggressive models. If we look at 2060, we see a big change there. We see a huge increase in the number of 100-degree days. But I'm going to focus on the 2100 here. And so you see there a lot more of the map has the hot colors on it, and focusing here on the Southeast. And I'll point out some numbers that are just pretty unbelievable. They happen to point out Fredericksburg, Virginia, which is projected to get 52 days with the temperature. I believe that should be 100 degrees and greater. Okay, and even all the way up in Philadelphia, 28 days. Very interesting, Atlanta, which is far to the south of Virginia, only projected to get 39 days. It's a bit cooler there, and I'll say too, a little bit about the climatology of heat. When you get up in the Carolinas and up into Virginia, you have the southern Appalachians here, and when you hit the very hottest days, you have winds that cross over the mountains. and that air comes down and it compresses and it gets hotter. I mean, this effect is especially felt in the DC area, but it's experienced broadly through much of the Carolinas and the rest of Virginia there as well. So that's really the most dire scenario. And I'm not saying that's going to happen, but it's much more likely to happen if we don't make some really major changes in how we do certain things there. Okay, so let's go in now to measures of heat stress. We're all very familiar with air temperature, and I think most of us are quite familiar with humidity. And so when you put those two together, of course, we have the heat index. And the heat index is used very widely in the Southeast U.S. because, of course, we have a whole lot of humidity, lots of days that are quite warm and humid. And so that provides a better measure of heat stress. But by far, though, the best measure of heat stress is one that incorporates not only those two variables, but also wind speed and solar radiation. And so wind speed, we can think of that in terms of ventilation. That's why we have fans. And I'll show you a little bit later that just increasing the wind speed by 2 miles an hour can have a very marked reduction in the amount of heat stress, or specifically here, wet bulb globe temperature. And of course, the fourth factor that's very important, it's rather obvious. If you're out in the sun, it's going to feel a lot warmer, and it's much more dangerous. And so the wet bulb globe temperature very effectively takes that into account. I will also say, and this is very relevant in urban areas, is that you have an urban landscape that effectively absorbs a lot of solar radiation during the day. And so it's radiating out what we call infrared radiation. And so if you're out in the sunlight in an urban area and there's a lot of asphalt around, particularly building materials that have a darker color, they're of course going to be very hot. And so they're constantly radiating out. And so that can greatly increase the wet bulb globe temperature. And so you can have very local places and cities where the wet bulb globe temperature is extremely high. We're going to be doing some field work in Charleston, South Carolina this summer, looking at that, and also looking at complexities with the sea breeze that comes through there. But where there's lots of moisture coupled with with an urban landscape, and I hypothesize we're going to find some ridiculously high values of wet bulb globe temperature. Okay, so I don't have time to go into all the details here, but I just want to show you here briefly an actual wet bulb globe thermometer. This is a Quest thermometer. It costs on the order of $3,000. So it's in the upper, you see it there on the upper right. And it basically is measuring temperature 3 different ways. It measures temperatures sort of in a regular way in what's called basically the dry bulb, basically the dry bulb temperature. But it also estimates humidity and wind and radiation through something called the natural wet bulb temperature. And then you see the black bulb that's on there. I mean, that's where the globe, the center of the globe gets its name. That black globe absorbs much of the radiation, almost all the radiation coming in. And so that effectively incorporates radiation into this measure of wet bulb globe temperature. So this is an expensive device, and so too expensive for most people to purchase it. And so fortunately, we have a number of instruments out, and I show you one that I think is the most popular, the Kestrel 5400. And it cost, I think, almost $400. So it's nearly an order of magnitude cheaper. It's not cheap, but a lot of high schools now have purchased these, and they're required to do so. I'll say more about that here in a few minutes. But it's not an actual wet bulb globe thermometer, but it makes very, very good estimates of wet bulb globe temperature. Okay, so many states have developed requirements for high school sports practice around wet bulb globe temperature. So they actually require the high school to go out there by the practice field, set up a wet bulb globe thermometer and measure it. And so they have what they call flag levels. And so basically it's a white flag if the wet bulb globe temperature is less than 80, green flag if it's between 80 and 85, et cetera, going all the way up to 90. Now these guidelines vary across states, and what I'm showing you here are the guidelines for North Carolina. The guidelines for South Carolina and Georgia are slightly higher, which is very, very interesting. So there are some disagreements, and some of this has to do with the climatization, but in Georgia, the athletic department there says that black flag is 92 degrees or higher, and that 92 or 90 in this case is very significant, because if the value gets to that or higher, you're required to completely suspend the practice there. And so acclimatization is a huge, huge factor in heat. And I don't have time to get into that, but I imagine a lot of you have some familiarity with that. Now, OSHA also has very strict guidelines for worker exposure to heat stress. So they have a detailed table here that's basically oriented around the level of work. So easy, moderate versus hard work, and that's described. And so they have basically guidelines you see there for the different flag levels. And their scale is slightly different than the other one there that I was just showing you. Okay, so let's move now into kind of this little bit of a climatological background looking at the entire Southeast. So we're going to look at regional patterns of heat stress, wet bulb globe temperature. We're going to start off with these components that I was just telling you about that are factored into wet bulb globe temperature. Now, the number one factor, of course, is temperature. And so you see here this map. This is really a state-of-the-art map. So it's a high-resolution map that does a very good job of depicting variations in temperature. And the values don't matter so much as I just want you to really see the pattern. And no surprise, the farther south we go, the warmer the temperatures are. I should point out that this is a May to September average. So that's 1981 to almost to present. It doesn't include this summer. Okay. But what I really want to point out is this area where it's the warmest. So in South Florida, the temperatures average out to be the warmest. And that's mostly because down there, their heat season is much longer, right? So they're in the low latitudes. But what we can see here, though, is basically an axis going in Georgia. So basically South Georgia and going through the Midlands of South Carolina, and then going right through the Sandhills and parts of the intercoastal plain of North Carolina, and then going into Southside Virginia and Tidewater, Virginia, and it continues up here into Delmarva. So that's basically the area where temperature is the greatest, but of course, again, they're increasing as we go to the south. Now, dew point temperature, that provides an effective measure of how much water vapor is in the atmosphere. So that's humidity. And what we see there on average is that humidities increase as we get close to the coast. And of course, that makes sense because most of the water vapor that we have in the atmosphere originates from the ocean. And the prevailing winds during the warm season are basically from the south to the southwest. So a lot of the air today, so where I am, the dew point right now is in the low 70s. And I will tell you probably quite a bit of that moisture is from the Gulf of Mexico. Sometimes our winds come around more from the south or the southeast. And so we can get a lot of Atlantic moisture coming in. But anyway, proximity to water really correlates a lot there with how much or how high the humidity is. The two other factors that play into wet bulb globe temperature, solar radiation. This is a very interesting map. And it was a map, I wasn't really sure exactly what the pattern would look like until it was produced. But generally, it's a little bit more complicated. But what it shows is this zone, basically very similar to the zone of highest temperatures going from South Georgia up through, again, Midlands of South Carolina, eastern third of North Carolina. And then it really maxes out. And I was really surprised to see this. I mean, and this area here in Delmarva really gets a lot of sunlight. In other words, they don't get clouds as much as areas to the west. And if you look closely, you can see the imprint of the Appalachian Mountains. So of course they start here in Western Virginia, but we have a lot of days where the winds are blowing out of the southwest and they basically curve around like this. And so you get upsloping. And so more of those clouds are going to be on the west side of the mountains and in the mountains, but they see more clouds. And so consequently, there's less solar radiation. And so that means that wet bulb globe temperatures averaged out are going to be a bit lower there. And then finally, wind speeds. It's interesting. We have the same area here again, where the wind speeds are higher. So there's a lot of agriculture, and it's a little bit hard to see, but this does extend up into far southeastern Virginia, and it goes up into Delmarva. So there's a lot of agriculture here, a lot of open fields. And so that's actually positive in terms of wet bulb globe temperature. There's more of a breeze on average. So there's not as many obstacles in the environment, trees and buildings and so forth to slow the winds down. So there's more of a ventilation effect. And so that does take the edge off of wet bulb globe temperature and heat stress there a bit. Another thing I'll point out, it's really kind of hard to see, and the map doesn't really do it justice because it only incorporates pixels of land, but it goes way up right along the coast. You can kind of see it up here. But of course, being at the coast, let's say literally on the beach, you get a sea breeze. And so oftentimes the wind during the day is coming off the water and there's nothing to impede that wind. And so it's a nice breeze. And so it really, it's perfect ventilation. So that markedly reduces the wet bulb globe temperature there. And we get in areas in the mountains, particularly really rugged terrain, that does slow the winds down a bit, just the terrain itself. And of course, there's a lot of forests there as well that slow the winds down. Now, fortunately there, temperatures are lower. There's not as much solar radiation on average. So it's not much of an influence there. So putting all this together, this is just basically a map that shows the patterns of wet bulb globe temperature. And so, so what we see, and again, so this is average May through September, but averaged out, the highest levels of wet bulb globe temperature are in the very southern areas here. Okay, and a lot of this, of course, again, has to do with temperature and that they have a longer heat season. But one pattern you'll notice here is that wet bulb globe temperature is higher inland. And so there's breezes along the immediate coast that really reduce that quite a bit. And there's even little blotches of yellow that you can almost see here, where basically along the Carolina coast and to a lesser extent going up in Virginia, you see relatively low values around the immediate water, but you go inland just a little ways and the average wet bulb globe temperature goes up. And so about every day, you're gonna see this pattern to varying degrees where it gets more dangerous as you go inland. So as you get away from the sea breeze, and as you get into forested areas or cities where there's lots of obstacles, the wet bulb globe temperature really increases. And the relatively safe places to be, of course, are the mountainous areas here, particularly the high elevation areas on the Allegheny Plateau here, and parts of the Cumberland Plateau, and then the high mountains here in western North Carolina and far southwest Virginia there. Okay, and this is just another map. This shows the pattern. This is just the month of July, which is ties for August as having the highest wet bulb globe temperatures. I'm gonna go back and forth there. You see, okay, it's basically the same pattern, but what I want you to notice is in July, there's not much difference between what we see basically in Eastern Virginia versus what we see in Georgia or Florida. It's dangerous in Virginia with wet bulb globe temperature, okay? And it's not much more dangerous when we get down into the deep South. So, you know, looking at this, you would say, well, okay, there's not as much concern in Virginia. Well, there isn't when you look at the entire heat season, just simply because it's a shorter heat season. But when you get into the core of the heat season, it can be really dangerous. And one thing I haven't pointed out yet, I was showing you some projections of heat, but I will tell you temperatures are they're increasing in the summer. And particularly at night, they're not cooling off as much. Okay, so now let's zoom into the local scale. So we see these broad scale patterns of wet bulb globe temperature. When we go down to the landscape scale, and I say here, consider a high school campus, because that's where much of our work has been done. But the work to this date that we've carried out shows very effectively that asphalt and concrete is the hottest, especially if it's dark colored. We've looked at turf fields and natural grass. And turf is really hot. And so that is a real concern. And so it's interesting, some of the high schools that can afford this, it's not a good idea. And they don't necessarily want to practice on it too. They don't want to tear it up. But turf can be very hot because turf is dry. And so natural grass is undergoing evapotranspiration. So that provides a bit of a cooling effect that you see there. The degree of shade, of course, really matters a lot. And so, you know, we're talking about, you know, areas that are shaded most of the day. If you go into a forest, it's markedly cooler. I'm a runner, and, you know, even on some of the really hot days, if I go into a forest, it really feels a lot cooler. And that's a radiation impact there, not just because I'm in the shade, but because the underlying forest surface, it's moist. And so there's evaporation taking place. So that provides some cooling. But in addition to that, that surface is cool, which means that it's not radiating as much infrared, okay? And so couple all that together, wet bulb globe temperature can be a flag level or two lower in a forest compared to even a shaded area, basically that wasn't, let's say, for example, that wasn't shaded earlier in the day. Okay, and a third factor, and it's a huge one, is the openness of the landscape. I've already mentioned it. So cluttered landscapes where there's lots of trees and buildings, it's going to tend to be the hottest because that's where you see the lowest wind speeds. And that is relative, and compared to open landscapes, that's where it's going to be the coolest. And I'll provide two examples, but first off, I just want to show you this plot here that demonstrates a two flag difference. It's a little bit of a complicated plot. I won't go into it, but this just takes a typical day. This might be a typical day, let's say, in Central Virginia, let's say in mid-afternoon. The temperature is 86, it's humid. It's one of those dog days. The dew point is 70 degrees. Okay, and if the wind speed is blowing 2.5 miles an hour, that puts it into the yellow flag. So that would be about 89.5 degrees. And if the wind speed then just goes from 2.5 miles an hour down to 1 mile an hour, that puts it squarely in the black flag. Okay, so just a 1.5 mile reduction in the wind speed markedly increases the heat stress there. So ventilation is absolutely huge here. So this was really borne out in some field work that we did before COVID. This was the summer of 2019. So we went to about 7 different high schools. We made measurements. We also, we didn't know we were doing it at the time, but we were basically deputizing basically athletic trainers. They're the ones that, for the most part, are the ones that are charged with measuring. So they go out and they measure wet ball globe temperature, and they inform the coaches and the athletic director what the conditions are. And they're the ones that say, okay, it's too high, you got to stop practice and that kind of thing. So this high school, Eugene Ashley High School, it's in the Wilmington area. It's Carolina Beach. As a crow flies, it's probably only about a mile, literally, from the beach. The beach is off on this Google map here. Whoops, is off here to the east. But you see here from the Google map, there's a very open landscape, particularly to the east of the practice field that you see here. They get really good breezes. And while the humidity can be wicked there, okay, and you can get real high heat indices, you do get a cooling influence. The air, when the sea breeze kicks in, the temperature is slightly cooler, but the big thing is the breeze there. And so it can be really dangerous, and they've had to stop practices there, but it's not, considering its location, it's not too bad. Now that's in polar contrast to Cedar Ridge High School in Hillsborough, Virginia. So this Google map here, and it doesn't really do it justice, the practice field is in a pit. Okay, you can't see it here. This is the practice field, but what you will notice is it's almost completely ringed by trees. It's down in a low-lying point there in the landscape. And we went down there, you know, and took some measurements, and we were talking to the trainer who was telling us the first time we met her, she said, I think there's something wrong with my kestrel, because there are days in which it measures 97, 98 degrees, which is ridiculously high in the wet ball, you know, in the black flag category. So anyway, it turned out her instrument was fine, but it was one of those local places that's extraordinarily hot. And a lot of that had to do with the fact that there's virtually no wind there. And it's markedly better when you get up to the tennis courts, even though there's trees there, just being up a bit higher helped. It's still dangerous. And then up here where the actual high school is located and it's open, the wet ball globe temperatures there are like on the order of another 1 or 2 flag levels below. So there's 3, perhaps up to 4 different flag level differences depending on the day between being in this pit here and being here. So anyway, this is just testament to the huge role that landscape applies there. Now, we first went there in the summer of, I believe it was 2018. It was very, very wet here. And there were these wetlands. And so the humidity levels were also very high. So it was an absolute worst case scenario. And you see here, this is I-40, very close to where it merges with I-85. This is close to Durham. And so you get a lot of traffic here too. So, you know, the air quality, I imagine, is not very good in this area as well. So this is not a healthy place. Okay, so now I'm going to move into heat stress, and I'm just going to start off with some sort of definitions here. So heat stress, you know, so we have defined it here. It's the amount of heat from the environment that can affect us, okay? And that's wet ball globe temperature. Well, heat vulnerability is the likelihood of an individual or a population being injured by the heat. And there's 2 factors that tie in here. The first one, and a lot of you are going to be very familiar with it, is the heat strain, which relates to a person's physiological state. Okay, so basically their overall physiological response to the heat stress. And we know that's a function of their age, their state of health, medications they might be taking. Are they dehydrated? that can, so the heat strain can be much greater, obviously, if they're losing that ability to perspire. And the second factor, and one you might not readily think about, but one that's really came onto our radar, is exposure. So what is the level of heat stress somebody's exposed to, but very importantly, how long are they exposed to? If it's a few minutes, that's not too bad. But if it's an hour or 2 or 3, unquestionably, there's an additive effect there, right? And of course, that's where it gets to be very important to be drinking water frequently and also watching out for symptoms of heat illness. Okay, so we undertook a study here in North Carolina several years ago. We're actually in the process of updating it. We have a lot more data, but we got access to a syndromic surveillance system referred to as NC Detect. And it's a virtual census of emergency room visits across North Carolina. You see the map there on the bottom. So it's basically every hospital in North Carolina, with exception to, I believe it's 2 military hospitals, and then there's 1 hospital in Cherokee, so a Native American hospital. So they weren't able to get data from there. So it's basically provides excellent coverage. And we're very privileged that we were able to get age, gender, the date and time of the visit. We got data basically from, at the time we called it the ICD-9 codes. We've combined that now. I won't go into the minutia of that, but we got, very importantly, the zip code and the county of residence. So this is the billing, basically the billing address. And the zip code was huge because that allowed us to really drill in geographically to look at rates of heat illness. We also got insurance information, and to this point, we haven't done too much with that. So here's the map that shows the patterns of heat illness. And I think what really matters here really is just the relative differences that you see here. And so of course the red areas are the areas where the rates are the highest. Blue is where it's the lowest. And so just a little bit about the geography of North Carolina, if you're not too familiar. The black circles indicate bigger cities, okay? And so we got Gastonia, Charlotte. We go up here, we've got the triad here. So Winston, Greensboro, High Point, of course, the triangle, Raleigh, Durham, and then Cary here. But by and large, what we see is in the urban areas, the rates of heat illness are much lower than they are in the urban areas. So you see a lot more of the blue and sort of the pale yellow there in urban areas and the areas that surround it. But the areas that are extremely rural is where we see basically where we see the highest rates. There's a skew here to this area, which no surprise, I was showing you the climatological maps of wet bulb globe temperature. It is the greatest across the coastal plain, at least going inland a little ways from the coast. And so that's where the rates of heat illness are the highest. Okay, now there's other factors that come into play here. And a big one that we discovered was that there's much agriculture. And this map's a little bit hard to see, but this map basically shows the percent of the land that's devoted to particular classes of crops. And I want to focus your attention on fruits, nuts, and vegetables. And I highlight this area here where you see a lot of that in the coastal plain of North Carolina, the coastal plain of South Carolina. And I know we have folks from Georgia on this, so basically portions of South Georgia, there's a whole lot here. Now, some of that is labor intensive, okay? Blueberries, for example, Bladen County, North Carolina, there's a tremendous number of blueberries that are cultivated, and it requires human hands. It's not economically efficient yet with the machinery. It is too expensive. I guess I also want to point out the area here where heat can be dangerous going up into Delmarva, Virginia, and also the Tidewater or Southside, parts of Southside. I guess this would be more Tidewater, Virginia here. So this whole area, there's a lot of people who are out there. There's a lot of basically outdoor laborers, okay? And we've gone down there and we've engaged with folks, and that, that very much is the case. And I guess one thing I will point out here too, that the rates that I was showing you here are unquestionably underestimated because we're not taking into account people who go to urgent care or go to a doctor's office, and also many people who have heat illness who just don't go. And of course, we have a lot of seasonal workers, also undocumented migrants. And so they're going to be the last people to go. And very sadly, they can be the ones, that need it the most. And a lot of that too is around, and I won't go too far into this, but of course you get paid by how much crop you're able to pick per hour. Okay, so there's a very strong economic incentive to pack as fast as you can, and generating basically more body heat, so making you more prone to heat illness. So it is a huge problem, and it is a problem that's getting worse as the climate continues to increase. Another factor is that there's a lot of poverty in these areas, okay? And so this is a map that shows the percent of people living in poverty. And so we're seeing in these areas, it ranges from 20% to upwards of 33%. So it's up to 1/3 of the population in some of these counties is living in poverty here, okay? And so that is really problematic too, because oftentimes they don't have proper health care. They're less likely to go to the emergency room, if they have a problem. Now another one, and this is a very interesting one and a sad one. So this is a map here showing the percent of homes that are manufactured. And so from this broad perspective, you can see here, so from Georgia going up through much of the Carolinas, and then the same general area here in the coastal plain, North Carolina, and then going into here and going into Southside Virginia here. So you see a lot of mobile homes. And a lot of these mobile homes don't have very good insulation. They're going to have window air conditioners, which are not very efficient. And these are units too that burn a lot of electricity, right? And so consequently, related to that is that we have areas, and it's a real patchwork pattern here, areas where there's a lot of energy poverty. And so energy poverty is defined by the proportion of household income on average in a county that's devoted to energy costs. So you don't make much money, and the cost of electricity is higher. And I was astounded when I learned this several years ago, that there are huge differences in the rates of electricity in some of these rural areas. I mean, some of them it's relatively cheap, like it is in the urban areas, but there's other areas where it is extremely high. And so anyway, that's pointed out here very well on this map. I'll point out this area here up in northern North Carolina. I would hypothesize that this extends up into Southside Virginia here. And I know I grew up in Roanoke, Virginia, and so I know a lot about this area. And so I know there's a lot of poverty in this area. And so there's also too, and I didn't mention it, tobacco is another crop that requires at particular times of the growing season a lot of labor. And so we hypothesize that that's playing a role in some of these patterns too. And I'll just go back real quickly to this map, and you see some patchwork of counties up here, even extending into the Piedmont of North Carolina, that have high rates. And that correlates very highly with the amount of tobacco cultivation. Okay, so we have found through our research that there's a strong relationship here between temperature and heat-related emergency room visits. And I'm kind of looking at the time here, so I'm just going to point this out. We know there's a strong relationship. The relationship is a little bit stronger. It doesn't show well in this diagram, but it's a bit stronger with heat index. We're now doing this with wet bulb low temperature, and our results show the relationship gets even stronger. So the higher those values get, the more there is. I will point out that when it gets really, really hot, the rates go down, okay? Because it gets so hot that people say, I can't be out here. And so a lot of people mitigate, and they go inside, or that, they curtail their work activities. Now, what our study showed here is that the highest rates of heat illness are not with the young and elderly, which is what you traditionally see, but rather it's ages 18 to 34 years of age, okay? And so this corresponds very much not to a person's physiological state, but rather to their exposure to the heat. And so this is really borne out here when we compare by gender. So males, the rate for males is 3 times higher than females, because a lot of outdoor workers happen to be male, okay? And I bet this is underestimated even more, because males have even a less tendency to seek medical treatment, if they're suffering from something. We looked here real quickly, teenage rates of heat illness, and we found an interesting pattern here too, is that when we looked at the entire population, we saw that they peaked in July and slightly lower in August. But if you look here, if we just look at the 14 to 17 year group, August really stands out like a sore thumb. And where the the rates of heat illness are highest are very much in the rural areas. We hypothesize here this has to do with the beginning of the fall athletic season, okay? And particularly the first week when athletes are not yet acclimatized to the heat. Okay, so we've done a lot of work here. So we've done a lot of field work. You can see the picture there on the left. We've also had a number of engagements with personnel from high schools, so coaches, athletic directors, athletic trainers. We have a tool that I'm going to show you here in just a second. And so when practices were active in the summer, we got quite a few hits. So you can see it down there in that panel. The biggest hits, of course, were in the urban areas where there's a lot more people here. And we're hoping this summer, we're going to see a lot more use. We're going to be mapping it across the Southeast. Our tool the last couple of years, the geographic domain was just Virginia and North Carolina. We've extended it across the entire Southeast. Okay, and so this is the tool here. So this is I'm going to brag about it, is a very sophisticated tool. It takes digital forecasts from the National Weather Service, what they call their forecast grids. These are hourly forecasts, and we take their hourly forecast of temperature, humidity, air pressure, wind speed, and degree of cloud cover, and then we get from a separate site the sun azimuth angle, so the angle of the sun relative to the horizon. And we put it into a very sophisticated iterative routine to come up with a very good estimate of wet bulb globe temperature. So in that way, we generate forecast of wet bulb globe temperature. Okay, and so this is a screenshot here of the tool. Okay, and you can check it out. I checked it out yesterday, and I put in here Richmond, Virginia. Okay, but just real quickly, the interface here. So basically, so it's something you can access via our website, which I have the link to. But we have up here at the front, we have a lot of basic information. Basically, what is it? You know, how to use the tool. We're going to make a video here very soon to literally show you how to use it and how to correctly interpret the output. But what you have here is a Google map. And if you know where you are, you can click your location. If you don't know where you are, which sadly is the case for more and more people, you can put in your location. And this is, you know, with Google Maps, I mean, you could put in, if you're a high school director, you just put in the name of the high school, okay? And then you just basically hit the submit button, okay? And then a forecast gets generated here. And so I'm showing you here the forecast for Richmond, Virginia, and I'm gonna make this bigger so you can really see it. I did this yesterday, okay? And of course, today is Thursday. Okay, and so what we have here basically is we see here the prediction for Thursday. So we have more clouds today up in Virginia. When we go back, basically, this would have gone back to Tuesday. It was touching the black flag levels there. And so this starts off with basically the last 24 hours, and then the dark black here is roughly when the forecast was issued. So I grabbed this forecast yesterday, which was Wednesday. So black flag or red flag was predicted to be the high there. And so anyway, so we have this forecast that extends out to 5 days. Fortunately for most of us in the Southeast, we're really going to be in a cooling trend, and we're already, you know, seeing more clouds, particularly up in Virginia today. And you see the wet bulb globe temperatures falling off here. But you can see here where this is really useful for high schools. And we also put here the scale. So you see that's on there as well. I just couldn't fit it in. And so you see the levels there painted in the background. Another feature that we have here is we have this gray area, and I'll just use it to illustrate for the forecast today. The gray area shows the range within which wet bulb globe temperature could vary depending upon how much sunlight there is. So if there's full sun, no clouds for an hour or more, then you would expect the wet bulb globe temperature to be up at the top of this gray envelope. If, on the other hand, it's completely cloudy, you would expect wet bulb globe temperature to be down here on the bottom end of the envelope. And from engaging with the high school people, we learned that they have some degree to mitigate. And one of them is that they can choose to do some parts of the practice in the shade if they have it, particularly when we get into September and shadows are getting longer and they decide to delay practice an hour or two. Some high schools have the luxury to do that. Some in the rural areas don't, because actually some of the people playing football actually have to go to a job in the evening, you know, just to make ends meet. But at any rate, high schools have some ability to adapt. And one way to use this tool is to think about, well, where are we going to practice? If we can practice in the shade, we can see what it is here. If it's cross-country practice, like, well, if we can find some woods to run in, then we can see that we can really reduce the heat stress here quite a bit by running there, basically running in the woods. I'll say here too that when you can delay practice an hour or two, that's very useful. So if you're looking at this here and it's like, okay, we got this peak predicted for the late afternoon. This solid line here is 6 p.m. But we see, according to this, that the wet bulb globe temperature is really going to go down several degrees, predicted to go down several degrees in the next hour to two. So if we delay practice an hour or two, it's not going to be as bad. And so anyway, so they can use the tool in that way. And also high school coaches find it useful because they can look, say at the beginning of the week, or even look on Sunday and see what the week's going to be like and decide, what day are we going to have our most rigorous practice. If we're going to do strength training and we're going to do it, we're going to do it inside, maybe we can select the hottest day to do that. Okay, so our current work is to tune the tool to the local landscape. And so we've gotten some very high resolution satellite image where we can estimate how rough the surface is and really get down to the local scale to estimate wind speed, which I've shared is the big factor that controls it. We're gonna have some engagements, virtual engagements with high school athletic personnel on the use of the tool. We're also, the tool is available for the entire Southeast this year. It's going to be expanded to the whole Eastern U.S. May of next year. And we're also going to expand the tool to other sectors. So right now it's geared to high school athletics, but we want to gear it to outdoor workers. And then of course there's other groups too that certainly would find this useful. Okay, so my apologies for going a little bit over, obviously a whole lot to talk about. There's lots of acknowledgements here. So this has been very much a team effort. Some of the maps I showed you were composed by Jordan McLeod. Sandra Rain has accompanied me where we've done a lot of engagements. William Schmitz has been there. He's our service climatologist, so he's answered calls and so forth. We've been funded a lot through CISA, and one of my PhD students, Jordan Clark, he's the one who's done much of the field work on it. Also, the North Carolina High School Athletic Association has really been invaluable in inviting us in to do the engagements. And lastly, a former PhD student, Maggie Sugg, who's at Appalachian State now, she did a lot of the work looking at heat vulnerability. Okay, so with that, I'll stop my screen share. So thank you very much.
Thank you so much, Chip. That was really fantastic. A great overview and very timely as we head into these next summer months. I'll wrap us up very quickly here so we can get to Q&A. Please remember to put your questions in the Q&A box. I see that we have at least 3 already that we will get to momentarily, but just very quickly wanted to cover a couple of advocacy action opportunities here. We have our Virginia call to action on climate, health, and equity for any health professionals in Virginia who have not signed that already. We also just recently launched and wanted to draw your attention to the Virginia Medical Education Collaborative on Climate and Health, which is various medical schools in Virginia that are coming together to try and incorporate climate curriculum into schools of health training throughout the state. And lastly, just that you can always donate to support our work and the work of other CCAs, Clinicians for Climate Action in the other states. I'm sure they have information on their websites that we'll try to include in the future as well. And then just to remind everyone quickly that CME instructions will be coming through email tomorrow. I should also mention very briefly on the topic of heat that VCCA has been working the past several months to develop an infographic, which we're going to make public in the next couple of weeks to try and raise awareness about the dangers of heat illness in our changing climate and provide some strategies and tactics and education for young student athletes and athletic trainers. We'll be very excited to launch, so keep an eye out on our website and in our newsletter for that announcement in the next couple of weeks. And with that, we will open it up for Q&A. Dr. Conrad, if you can see the Q&A box and want to go through the questions and comments that have been submitted, you should feel free.
Sure. So the first question is, are storms getting stronger? And And I would say that it's not real clear. I will tell you that there are certain types of storms that may be getting stronger. And one of those are what we call derechos. And some of you probably are familiar with that term in Virginia because there was a major one that hit about 10 years ago. So it appears, and there's still a lot of research needs to be done on it, that with increasing temperatures, that provides more energy, and with the atmosphere slightly more humid, but we need to have the dynamics with that too. So it's a complicated relationship, but some of these very organized storm systems, it appears that they could be becoming more frequent. It isn't clear though that we're just seeing more pop-up storms, that are getting stronger. Okay, but there's a lot of caveats with that. The second question is around artificial turf. Just a comment, artificial turf also has all those little black beads to help hold it down and maybe provide cushioning. And that's a detail I wasn't aware of, but probably at least in a small way, because they're black, that's going to decrease the reflectivity. So that means that will certainly aid in causing the turf to absorb a little bit more of the solar radiation coming in. And then the third question, can you post the link to call to action in the chat? So I don't know, that's questions directed to me.
Yeah, we've posted that link in the chat, and Dr. Conrad, if you click on the Q&A box, you can see a few additional questions that were submitted that way.
Okay, so I was just looking at the chat. Why don't you read those off, because I don't readily
Sure.
See that.
Yeah, the first one comes from Sheila Stone, who asked about how the Appalachian Mountains make heat days increase. That seems anti-intuitive.
Indeed, and that's a good question, and I just touched on it. But in the mountains themselves, as you go up in elevation, of course, it gets cooler, and that was shown very clearly on the maps. However, the presence of those mountains, when the winds on the hottest days, and this is very true in Virginia and somewhat in the Carolinas, not really true in Georgia, but the hottest days, the winds are blowing largely from the west. And so those winds come down off the mountains, okay? And when the winds come down off those mountains, the air gets compressed, and that compression makes the air warmer. And some of the hottest days in the DC area, you very much have this effect here, and it goes all the way up, going to go all the way up there into New England. So it's just what us meteorologists call a dynamic effect, where you just, when that air gets pushed down to the surface, it basically makes it hotter. Fortunately, on those days, the humidity levels tend to be a little bit lower, and they also tend to be breezy. That takes the edge off, but still, those are very, very dangerous days.
Great. And the next question is, with the G7 and COP26 coming up later in the year, how can we get world leaders, politicians to act quickly now on climate change and create policies and legislation to support all citizens and prevent or lessen heat stress and strain?
Yeah, and I'm not the expert to answer that question. All I can say is there's compelling climatological evidence that temperatures are getting warmer, and certain types of extreme events, particularly heavy rain and flooding, is getting worse. Sea levels are rising. I mean, this is a dire situation. And one thing here too is that we can do a lot. I showed you the one projection there of how bad it could potentially be if we don't do anything. But what it means if we really start doing things, if we really start reducing our carbon footprint, I think that we can really affect some changes there, so we don't experience such dire scenarios. How you convince people, and it's a wickedly complex problem, right? Because a lot of the CO2 emissions are coming from the developing world. So it is, that question is way above my pay grade, in terms of answering it, but we all need to be absolutely thinking about it and being creative about how we can respond.
Thanks. And I'll combine the next two questions. One is, where can we get more specific information in Georgia from someone living in Atlanta about heat illness? And the second is, can you describe how you've connected with high school athletic programs on this work?
Right, and I'll start with the second part here. So we have connected, almost all of our connections at this point have been here in North Carolina. So they have a very active high school athletic association. And so they basically invited us in. They said, hey, would you guys like to give a seminar on heat illness and the use of your tool? And so they invited in I think about 10 high schools. And it was a long period there. And this is when we were just starting, but we had a long time with them, and a lot of it was around learning more about their needs and their limitations in terms of dealing with the heat. And we also got very good feedback on the tool. So it was very much what I call an engagement, where we learned as much, maybe even more than they learned. But it really caught on fire because they spread the word to other athletic directors, coaches, and so forth. And so we found that we got a lot of use. And in some cases, we had turned the trainers who were largely charged with measuring wet bulb globe temperature, we turned them into citizen scientists. In other words, they were going around different places, different fields, measuring wet bulb globe temperature, and also even going off the fields just out of curiosity. And so when we made field visits, they were telling us a lot about that. The second question, I don't have an answer there, about that, except to say that the Georgia State Climate Office would certainly have more information. So unfortunately, I'm not tuned, and certainly to the Atlanta area. I will say I have a colleague, Andy Grunstein, down at the University of Georgia, who's done a lot of work in Georgia. So Georgia takes heat very seriously. And so there are a lot of folks down there, but unfortunately, I'm not connected with the ones maybe that could readily supply that information.
Wonderful. And the last question, and forgive my pronunciation here as a non-scientist, but are you aware of any work looking at how photovoltaic panels change ambient air temperatures and what wet bulb globe temperature? And if so, in what direction?
That is an excellent question. And I don't know the answer to it. And we can kind of think about it here that obviously they're absorbing solar radiation, right? So there's a cooling effect. And I think it would be fascinating, and I'm sure there's been research done on it in terms of green infrastructure, right? I mean, it's wonderful if you turn your roof, into a garden. That makes the roof a lot cooler, and that reduces energy cost. But even better, if you got solar panels around that, then you're collecting some of that energy, which you can use there, to provide cooling.
Great. And we just had one last question come in that I saw. Should TV and radio meteorologists start using wet bulb globe temperature rather than heat index?
I would say so, but I would say they need to really get trained on it. And one of the things I didn't mention, and you were probably thinking about it, it's like, well, it doesn't sound too hot. The wet bulb globe temperature scale is different, right? Black flag is 90 degrees, for a lot of things, and it starts to get dangerous a little bit at 80. And that as a Southerner, that doesn't quite jibe. Point being there is that people need to get used to that scale. So I think that's something, yes, I would advocate using, but first with a lot of training on it.
Thank you so much. Dr. Adut, would you like to wrap us up here?
Yes, and actually, before we conclude, Dr. Conrad, thank you so much for that. I really learned so much from your presentation. I'm curious, is the satellite or is the data or the projections from the satellite wet bulb globe temperature, how are they correlating with actual values?
Yeah, that's a good question. So one is this is work that we're doing right now with satellite imagery to try to get at the land cover. And that's actually one thing we're going to do this summer in Charleston, South Carolina, where we have that urban landscape. Now, another thing you mentioned, and you could go multiple ways with this, you're mentioning projections. So I wasn't sure if you were like talking about heat in the future, or if it was around.
Oh, the 1 week. The 1 week projection. Doesn't it project for the week?
Yeah, exactly. Yeah. Okay. Yeah. So that's definitely a forecast and
forecast.
Yeah. and really what you bring up is a great question there around, well, how good is this, right? We need to validate what is the skill of our model. One thing I'll tell you is I'll brag again, the National Weather Service has a crude model. It's an experimental forecast. I won't tell you where to get it because I don't think it's very good yet. And I don't mean put them down. They're working on a lot of things, but our model does quite well. And we just to kind of give you a ballpark sense, at 2 days out, it forecasted within one flag level 80% of the time. Okay. We've tweaked our model since then, so we know it does better than that. But once we include the satellite imagery and we can really drill in, I think, who knows? I mean, maybe we can get to 90%. And then it's like approaching an asymptote. I don't know that we can, because see, we're relying on National Weather Service forecasts too, which we know are not, they're pretty good, but they're far from perfect.
Obviously, when it comes down to canceling practices, people will I imagine, become rather eager for very accurate results, or it could get a little, and parents and coaches, it could get challenging, right?
Well, when we engage with them, they said, well, can you give us a thunderstorm predictor too? Because you have the pop-up storms, particularly in August. And I say, I'm no better in the Weather Service. I'm not even as good as the Weather Service with that. But that's one of the caveats with this model, right? Because the model is using these forecasts, and that's a bit that's not incorporated. And I'll say, well, that's one caveat with this model. And yeah, you need to be watching the sky, because even the forecast can be off on that.
Great. Well, I can see it's going to be an invaluable resource for schools and athletic programs. Well, thank you so much. And thank you all. It looks like we have a participant from London here. Well, wonderful that you could join as well. And Dr. Conrad, we look forward to hearing from you again in the future and learning more about your work in the months and years to come.
All right. Well, thanks again for the opportunity. Goodbye.
Bye-bye, everyone.